Today I'm going to walk you through an important and famous and sort of revealing derivation using the entropy from statistical mechanics, which isn't to say that you need to reproduce this derivation, but it's pretty cool. So we know entropy is K ln W, where K is the Boltzmann constant, natural logarithm of the number of ways to arrange a system. And we showed in class on Monday that that's K ln and then n factorial over the product of the AJs, where AJ is the occupancy of state J. Okay, so just doing some math here. By the rules of logarithms, the logarithm of a ratio is the difference of the logarithms. And then also by rule of logarithms, the logarithm of a product is equal to the sum of the different logarithms. So far this is all exact. So we're going from logarithm of a product to a sum of logarithms. Okay, and then there's something called Stirling's approximation. So this is an approximation, but the logarithm of x factorial is approximately equal to x ln x minus x. And this is very good for a large x, so I figured it out. It's 0.07% error when x is equal to 1,000. And if our x here is on the order of moles, so like 10 to the 23rd, then it's pretty much exact. So then our entropy is equal to K n ln n minus K sum of AJ ln AJ minus AJ. So again, just as a reminder, K is sometimes notated as KB, that's the Boltzmann constant. N is the number of molecules in the system, and then AJ is the occupancy of state J. And we're summing over J equals probably from the ground state to infinity. But of course, if we sum all the occupancies, that's just equal to the total number of particles. So we can rewrite this. So here's just the same thing rewritten again, taking out the K, but then substituting instead of N, sum over J, AJ. So because of that sum. So then now again I have the difference of logarithms, so I can re-express that as the logarithm of the ratio. And but then once I have that ratio, this is actually K times sum over AJ ln PJ, because PJ, the probability of being in state J, will be the occupancy of state J divided by the sum of all the occupancies, which is just the number of atoms. And then if I take the logarithm of both sides, the logarithm of PJ, which is the logarithm of, this is just the Boltzmann distribution. So then I get just, if I just take the logarithm of this argument, and again I've got a logarithm of a ratio, I can write as the difference of logarithms, and the logarithm of e to the negative capital E ej over kt will just be the negative ej over kt, and then minus the logarithm of q. So then putting it all together, my entropy is equal to sum over k, k sum over aj, and then I'm substituting in for ln pj this stuff. So then what do I have? Well, so then my entropy is equal to taking this kt out of the sum, because that's just constants. The k's cancel. I got 1 over t sum over aj ej plus k, then sum over aj ln q. But sum over j aj ej, that's just the average energy. So this is because I've got the energy of state J weighted by the occupancy of state J, so that's just a weighted average. So I'm just getting the average energy here for the molecules, and then I've got K, and this sum over AJ is just N, so then ln Q. Because, okay, now but for large N, my average energy, eigenvalue energy, is equal to the internal energy. So then really this is just u over t plus k ln q to the n. So again, using the properties of logarithms, instead of n multiplied by the logarithm, I can have the logarithm of q to the n. But of course, q to the n is capital Q. So now I have internal energy over t plus k ln q. Okay, why am I doing all of this? Let's continue. So the Helmholtz free energy, which is one of the 4 free energies that are introduced in Chem 317, and it's probably the one that's least talked about, but this is the one that's most important for statistical mechanics. So by definition, the Helmholtz free energy is the internal energy minus temperature times entropy. So then this is U minus T, and then I can just put in my expression for the entropy here, U over T plus K ln Q, and the T's cancel, and then the U's cancel, and then the A is just negative KT ln Q. So I can get the Helmholtz free energy directly from my canonical partition function. And remember, my canonical partition function is directly from the molecular partition function. Remember, the molecular partition function is directly from the solution to the Schrodinger equation, because right there you have the eigenvalues. So wow. So we can get the Helmholtz free energy for our system ultimately from the solution to the Schrodinger equation. I mean, that's incredible. That's incredible. But wait, there's more. Because the pressure is just the negative partial derivative of the Helmholtz free energy with respect to volume at constant temperature. And you can get this from this mnemonic, which maybe you had in Chem 317, maybe you didn't, but volume, Helmholtz free energy, temperature, internal energy, Gibbs free energy, entropy, enthalpy, pressure, dA dV at constant T is equal to negative P. And if you don't know how to use this mnemonic, that's okay. This is really more of a thermodynamics thing, but it is a pretty cool mnemonic, and if you'd like to know more, I can send you a reference on that. But dA dV at constant T gives you, going against the arrow, negative P. So P then is equal to negative dA dV constant T. So substituting in this for A, so then we've got negative d dV, negative KT ln Q, constant T. Well, if the T is constant, I can take that out of the derivative, so I got KT d dV ln Q, putting in Q to the N for capital Q. I can take the N out, so I got NKT d dV ln Q. But then remember, for the particle in a box, lowercase q is V over lambda cubed. And here's our lambda, our de Broglie, our thermal de Broglie wavelength. Notice this depends on just constants and temperature. So it's a constant with respect to T. So if I substitute this in and I break it out because I'm taking the logarithm of this thing, sorry, it's a constant with respect to V. So d dV, this is going to go to 0, that term. So d dV of this, I just logarithm of V, I get a 1 over V. So I get a P is equal to NKT over V. So in other words, PV equals NKT. And capital NK, if I multiply by the if I multiply the number of moles by Avogadro's number, I get capital N, and if I divide the gas constant by Avogadro's number, I get K. So the NA's cancel, and I get NR. So in other words, PV equals nRT. This is incredible, because what we've done here is we've directly derived the ideal gas law from the particle in a box Schrodinger equation. Ba, ba, ba. This is like the climax of the whole semester. So anyway, I hope you enjoy that. You can go from H psi equals E psi, and get PV equals nRT. And we can do similar things for other systems. So harmonic oscillator, rigid rotor, hydrogen atom, and for other thermodynamic quantities, so internal energy, enthalpy, constant volume heat capacity, constant pressure heat capacity. All of thermodynamics can be derived from quantum mechanics using statistical mechanics. And that's pretty awesome.